Hello everyone, John CFG here, and before we get the video started, as always, I'm going to give a quick disclaimer. Despite my YouTube username being John Teacher, I'm not a real teacher. I'm rather a student of computer science willing to work through a couple of practice problems. And before we get started on those practice problems, I'd like to note that our alphabet we're going to be working with today consists of A's and B's. With one exception, I believe that will be problem 4 today, which we will not use this alphabet for. But without further ado, today's topic is on CFGs, or in other words, context-free grammars. So let's get started. First, I'd like you to start thinking of the language for context-free grammars that contain A to the I, B to the I, such that I is greater or equal to than 0. And just a heads up, the way I'll be writing context-free grammars will be the informal way. There is a formal way, but not in today's video. So, for example, if I were to write S, any capital letter that I use is going to be the variable, and then any lowercase is going to be a character in our alphabet, and then epsilon will be sort of our terminating condition that represents empty string. And an example of a string that will be in this language that I made, which this doesn't solve the first problem, by the way. This is just its own little thing, just so we get with how my writing style is. So we start with S, we go to AS, AAS, AAAS, and maybe we terminate on the last one, AAA epsilon, but epsilon's really empty string, so it's really just AAA. All right, it could go S and immediately to epsilon. It could go S to, or oops, a little bit of a snake over there. S, AS, and then go to a epsilon, and then result in A. So that's how I'll be writing context-free grammars going forward with this video. So yeah, I hope you had time to think about it, if that was enough of an excuse, which I always encourage you to think about problems before you watch me do them. But yeah, so as always, we're going to start with the start variable. We note that A and B are both to the power of I, and I is greater than or equal to 0, so it can be empty. But the important part is that since they're the same variable both, is that however many number of A's we have is exactly the same number of B's that we'll have. So we're going to write it as such, ASB, and let's think about it. Start with S, go to ASB, AAS, BB, AAAS, BBB, 3 B's, 3 A's. The A's are on the left, B's are on the right. Looks good. One important thing, remember when I was going through that starter example, we need the epsilon, otherwise this just keeps going and keeps adding on A's and B's and resulting in a language of nothing. So we tack it on at the end. And that is the context-free grammar for the language of A to the I, B to the I, such that I is greater than or equal to 0. All right, let's go with the second problem. Second problem is the language of even length palindromes. And before we start, two things. One thing, this is for A's and B's. Okay, that is our alphabet. And if you don't know what a palindrome is, a good example of this is race car. If you were to flip all the letters, you would still get race car. And by flip, it's probably not a very good description. I don't know. If you had hello, flipping hello would mean, not sure what that word is, but yeah, that's essentially, this is what a palindrome is. If you flip it, then it could mean the same word front to back as back to front. Okay? So, I hope you had enough time to think about it. So, maybe we should start with a quick example. That might help. So, an even length palindrome might be A, 2 A's on the right, 2 A's on the left. And if we were to flip them, it would still result in A. Maybe we have A, B, B, A. If we were to flip them, it would be A, B, B, A. Okay. Another example, maybe B, A, B, B, A, B. If you were to flip them, then it would be B, A, B, B, A, B. So yeah, and think about how we built this, our first example, where we had a bunch of A's on the left, a bunch of B's on the right. In this example, there could be any number of A's on the left, any number of B's or A's on the right, and we need to be sort of keeping that in mind that there could be a number of A's on the left, number of A's on the right, but the only rule that sort of balances it all together is that the number of A's on the right is equal to the number of A's on the left, and the number of B's on the left is equal to the number of B's on the right. So, as always, start with our start variable, and if we want the number of A's on the left to be equal to the number of A's on the right, then we would write it as ASA. But that's not our only rule, because we could have B's in our palindrome too. Didn't need to do that. BSB, and then always our terminating case. So let's think about it. Just drag, sorry about that. Let's drag this one down. Start with S, A, S, A, S, A, A, and then A, epsilon, A, which epsilon is just the empty string, so we get that. Okay, and rules that I applied here, I read this for the first time, but probably not future problems, is that we start with S, we apply rule 1, we apply rule 1 again, we apply rule 3, and then we have our string. Let's take the big one. S goes to B, S, B, and then it goes to B, A, S, A, B, and then it goes to B, A, S, A, B, and then it goes to B, A, B, S, B, A, B, and then it goes to B, A, B, epsilon, B, A, B, which the epsilon cancels out, B, A, B, B, A, B. Same, it's a palindrome. Whatever's on the right is equivalent to whatever's on the left, so we're good. All right. Notably, I'm going to write problem 4 close to problem 3. Nope, that's not problem 4. That would be problem 3. I apologize. Problem 3 close to problem 2, because this is going to be the language of palindromes over the alphabet A, B. Okay? Now, what do I mean by this? Notice how race car has the car on both sides, but it has this E in the middle. It's still a palindrome. It's just an odd length palindrome. For example, if we have ABA and we flip it, it's still ABA. So that's completely valid. And we don't really have to destroy too much of what we had before. All we simply have to do is write ASA, BSB. But think about a terminating case. Did I ever, in CFGs in general, you don't specifically have to write a rule such that it either has to be empty string or some combination of something with S. So what we can do instead is terminate it with a B or an A or an epsilon, and that solves our problem. Because if we go to S and then ASA, and then we go to ABA, what rules did we use there? 1, 2, 3, 4, 5. We use rule 1 and then we use rule 3 to get it done. But yeah, that is the language of palindromes and the language of even length palindromes. And I will just box them in for clarity. Or I said box them in and I drew a circle. Oh well. All right. Number 4 is going to be the language of balanced parentheses. Oop. Sorry about that. Balanced parentheses. So, a common thing in programming, if you were to say, call like a, I don't know, maybe a Java function, you have like object dot function, and you had parentheses, but maybe inside those parentheses, you have other things like an array of I in those parentheses, and you just want to make sure that they're balanced. And what I mean by balanced is This is a set of balance parentheses. Like if you were to go through it on a stack, push this onto the stack. You see this, you pop the left one from the stack, and then it wouldn't be there. But I don't know. If you're confused, I'm sure there are plenty of videos out there to help you explain balance parentheses. If you want to think about it, I could write a couple down. This is a balance parenthesis. This is a balance parenthesis. This is not a balance parenthesis. What's another good one? This is a balance parenthesis. I'm trying to think. This is not a balance parenthesis because we need closers for those. But yeah, basically the language of balance parentheses. And we kind of want to think about it in similar terms. And I didn't mention this, but since we can't use A's and B's for balance parentheses, we could. For clarity, I'll make the alphabet for this consisting of these parentheses. So yeah. So typically S A or left parenthesis S, right parenthesis, okay? Epsilon, that seems like a good solution on paper. But remember is that this case is also possible. Let me explain this. So we have, or we don't start with that. We start with S, apply rule 1, apply rule 1, apply rule 1 again, apply rule 1 again, apply rule 2. But how are we ever going to get a rule like this? Or not a rule, a result like this? Well, a good way to think about it is that we can simply concatenate our start variable, S, epsilon. So I want you to think about this. Our goal, this is our goal. Goal is to get this, which this looks a little like an S, so I will fix that, sorry. Goal is to get this. So we go to S, then we go to SS, then we apply rule 1, S, then we apply rule 1 again, then we apply epsilon, well, no, I'll leave it in for now. We apply the epsilon rule again, and then because they're epsilon, we get this as a result. And if I said rule 1 right here, I don't remember, this is rule 2. 3. But yeah, this is the language for balance parentheses. Okay, that was problem 4. Moving on to problem 5. The language that contains exactly 1B. All right, so back to the alphabet of A's and B's for the remainder of this video. So, as always, we start with our start variable. But it contains exactly 1B. Okay, B? Well, no, it could contain a bunch of A's. Let's think about this maybe before we start. Let's walk through an example. Exactly 1B, we could have A, B, A, but doesn't necessarily have to be even. Could be A, B. Could even be B, A. Interesting, interesting. Could even be B. Can it be empty string? No, it contains exactly 1B, so it can't be empty string. That's important to note. It can be all of these. So yeah, think through it. Take 10 seconds. Come back to me with what you have. All right. Hopefully you spend time thinking about it. Start with our start variable S. And then we could have any assortment of A's, really, to the left of S. And what I'm going to introduce here is that you don't always have to have one variable. We could split this off into a second. So the way I like to think about this is we have some number of A's. Could be 0, could be a bunch. And then we have a B, and then we have some number of A's again. Doesn't necessarily have to be equal on either side for the number of A's, but let's work with that. So a bunch of A's get spawned in. Then let's say we find a B. Well, then B and X. And X is going to be our new variable defined. And then, I don't know, maybe we could tack on an epsilon to finish it. Because, we have A, and then C a B, and then we want to terminate. Seems perfectly valid to me. Next, X, and then, so what this represents right here is we're going to have a bunch of A's, maybe an S, and now we're looking at this portion of it. So what we want, ideally, is a bunch of A's leading to X's that could eventually terminate. Okay, and then this will populate this portion of the S. So yeah, it looks good. However, there's one tiny mistake with it, and can you think about it? Well, looking back at our examples, we notice that it cannot contain just the empty string. However, we've made it possible from our start variable to go directly to the empty string, which contains nothing. So, we can't have the empty string rule in here, or we can't have an epsilon there. Okay? But like we said before, it could contain a bunch of A's, S, and then terminate right there. Does it still cover that case? Yes. Goes through a bunch of A's, check. Grabs the B, check, and then can contain just an epsilon. If it only wants a B, it goes through a B, and then it goes to epsilon. So yeah, that is the language that contains exactly one B's for a CFG. And now, working on our last problem is going to be the language that contains an equal number, or I'll write number fully not to confuse people, number of A's and B's. Okay, so let's think about what we want here. B, A, B, A, B. Okay, we got 3 B's, 3 A's. Okay, seems like the same number. A. Yep. Or wait, no, equal number of A's and B's. I apologize. It should be B. Okay, equal number. What about B? No, not an equal number. Okay, So it could have any assortment of A's to the left and any assortment of A's to the right. Same goes with the B's, and we somehow have to keep track of an equal number of A's and B's. Now, here's something that I typically would recommend, though you have to be careful about it equally applying for all cases. So what we're going to do is we're going to start with our start variable S. And every time I place an A, there must be a B to follow. Otherwise, it can't be in the language. So A, S, B, right? Okay, but what if the B is to the left of the A? Okay, B, S, A. Well, that covers the case of like A's, B's, B, A, right? Covers cases like these. However, we also have to consider cases where maybe how do I explain this? If we were to divide this in half, okay, this A matches this A, right? This B matches this B. Like it's symmetrical. There, that's the word I'm looking for. It's symmetrical. And while that's a very nice property to have, our language just contains an equal number of A's and B's. So it doesn't necessarily imply that it's symmetrical. So a way that we could solve this problem is why is this not undoing? It's very unfortunate. Undo. There we go. Sorry about that. We've actually looked at this before, similar to the balanced parentheses, when we were having this trouble of symmetry, or just trying to get something outside of our artificial boundary that we made. We applied the concatenation of the rule S to solve this, and it can be used in the same way in this case. So we apply the concatenation of S, and then don't forget we always have to terminate it with an empty string. So let's go through some practice. Maybe A, B, B, B. Not symmetrical. See if our rule can be applied. I started by writing SS. Oh, went to the top again. Sorry about that. Still learning the iPad. All right, example. This is our goal. So we start with S, we go to SS, we go to ASBS, then we go to A epsilon BS, and then we go to AB because epsilon's the empty string S, and then we go to ABASB, and then we go to ABAASBB, then we go to ABAA epsilon BB, which because that's an empty string just simply results in the string that we want. So you can work through it. Pretty confident here though that we got the language that contains, or the language for a CFG that contains an equal number of A's and B's. And that will be the end of today's video. Thank you.